Hello, everyone. We're going over another example of how to go from a Latimer diagram to a Frost diagram. Again, we need to establish the oxidation states of the different forms of the element in question. In this case, I have a Latimer diagram or partial Latimer diagram for Cl. And so these are some oxidation states here for you. So let's start with the zero oxidation state, which is the Cl2 form, the elemental form. In all ions, the oxidation state is the charge on the ion, so this is -1. For the other two, they're combined with oxygen. So in this case, the oxygen is -2 in its compounds. So that must be Cl by default is +1. So they add up to give you the -1, which is the charge on the ion. Okay. And then we have ClO2. So we have two of the oxygens, which would be a total of -4. And therefore, the chlorine must be +3. +3 minus 4 equals -1. So we have a 2 electron transfer here. We have a 1 electron transfer here and a 1 electron transfer here. So Latimer diagrams are going down in oxidation number because they're written as reductions, okay, consecutive reduction reactions. Very good. So that's the first thing that we do. And we also establish that the X in the pairs for our Frost diagram must be the oxidation state. So we have a 3, a 1, a 0, and a -1. And our Y is going to be the oxidation number times the potential to get to the zero state. So for the zero form of the elements, always 0, 0. And the ones that are directly adjacent to it, that makes life easy. We have, for example, here 1.36 for Cl going to Cl2. Backwards, it would be negative, but the negative oxidation state actually takes care of that. So N is -1, and we multiply it by the 1.36. So this was for Cl2, and this is for Cl minus. So we have -1, and the Y is -1.36. Okay. And then we have the other side of Cl2, which is ClO minus. That data pair for our Frost diagram would be 1. And then it's directly next to the zero oxidation states. That would be 0.42. So 1 times that is just 0.42. By the way, these are in volts. I left off my units. Okay, so the last one would be the non-adjacent ClO2 minus, non-adjacent relative to the zero oxidation state. So we would need to figure out the potential between these two. Okay, non-adjacent, so that requires the formula. Remember, the formula is the number of electrons transferred in the first times the potential in the first pair plus the number of electrons transferred in the second times the potential for the second pair divided by the sum of the electrons transferred in the two pairs. So for non-adjacent species. So our non-adjacent species are the ClO2 minus and the Cl2. And we have two potentials here. This is a 2 electron transfer. This is a 1 electron transfer. So we have 2 electrons transferred in the first arrow, which is the 0.68 volts, plus 1 electron transferred in the second pair, which is the 0.42 volts. And we're dividing that by the sum of the two, which is plus 1, that's the 3. And I believe I already worked this out. Came up with 0.593 volts. Okay, so that would be up here for the non-adjacent species. Very good. So in order to get our Y for our frost diagram, then we have the oxidation number of 3 times the 0.593, which is the potential to get to the 0 oxidation state. Okay, and so what is that? I did not do that ahead of time. So our handy dandy calculator. Of course, I couldn't do that in my head, but I am being recorded, so I'm going to make sure to do it using the calculator. Okay, 3 times 0.593, and of course that is 1.779. Okay, we'll just call that 1.78 volts. Okay, so the units for the Y would be volts, and there's no units for the oxidation number. Regardless, these data pairs, the XY data pairs, will make up our frost diagram. And that's it.